So in the previous video, we have defined the intersection number modulo 2. Now, let's check if this definition is good. Let's see if it actually resolves the issue that we mentioned about homotopic map. Let's check that homotopic maps do indeed have the same intersection number. So let f0 and f1 be maps from M to N, and let's say that they are homotopic via homotopy f here. That is, f is a map from this product of the interval with M to N. And f0 is just going to be f at the level 0, f1 is just going to be f restricted to the level 1. Then let Z be a submanifold of N, and let all of these M and Z satisfy our hypothesis, this setup. Now let's assume that f0 and f1 are both transversal to Z. We want to show that the intersection number of f0 with Z is going to be equal to the intersection number of f1 with Z. First, by extension theorem, we can assume that this big homotopy map itself is transversal to Z. Now let's look at the preimage of Z under this map F. We claim that it's a one-dimensional manifold. So why is that? Well, by the transversality theorem for manifold with boundary, we know that this codimension is going to be equal to the codimension of Z inside N. And what is this? Well, by our hypothesis, M and Z are of complementary dimension, so this is just going to be dimension of M. Thus we have that the dimension of this product minus the dimension of this preimage is equal to dimension of M. But the dimension of this product is just dimension of M plus 1. So we see that the dimension of this preimage must be 1. And thus by our previous discussion on the classification of one manifold, we know that this preimage must be a union of unit interval or unit circle, and so its boundary must have an even number of points. But what is its boundary? Well, again, by the transversality theorem for manifold with boundary, we know that this boundary is going to be equal to the intersection of the preimage of Z with the boundary of this product. But now observe, the boundary of this product are just these two copies of M, the top and the bottom. Right, so this boundary, the boundary of the preimage of Z, is just gonna be the intersection of the preimage of Z with these two copies of M. But observe, the intersection of the preimage of Z with this top copy of M is really just the preimage of Z under f0, right? And then the intersection of this preimage with the second copy here, the bottom copy of M, that's just the preimage of Z under f1. For example, in this drawing, I illustrate this intersection by these blue points. And as you see there, the union of two parts, these top blue points are just the preimage of Z under this f0, and these bottom blue points are just the preimage of Z under this f1. Now, as we said, because this preimage is a one-dimensional manifold, its boundary must have an even number of points. That means the total number of blue points here must be even, and thus the number of blue points on top and the number of blue points at the bottom must have the same parity. They must be either both even or both odd. In other words, these two fibers have the same cardinality modulo 2. But remember, these two fibers are just the intersection number mod 2 of f0 with Z and f1 with Z. So we see that these intersection number mod 2 must agree. Thus, this definition of intersection number mod 2 does indeed fix our problem. Now the question is, did we sacrifice too much to fix the problem? There are only two possibilities for intersection numbers mod 2, so is that going to be nuanced enough to say anything interesting at all? Indeed, it's not the ideal, that's why we want to work with the oriented intersection theory, but you'd be surprised at the kinds of things that we could already said with just intersection theory mod 2. So we'll address that next.